I'm kicking off OSE seminar. Got it. So I thought it would be exciting to kick off OSE seminar by talking about a paper I published in December. It came out about 3 weeks ago at this point, entitled Dual Phase Shifted Ipsilateral Metachrony in Americamycis bahia, which is an extremely wordy and polysyllabic title, but it just boils down to shrimp swim, and this one swims weird. So let's talk about what exactly this organism does. I'm interested in multi-appendaged propulsion as an alternative design for AUVs, or autonomous underwater vehicles, like the device shown in this figure. Currently, these devices rely on a single propeller located at the back of the device for propulsion, and while this definitely works, if something were to happen to the propeller while the device is out in the field, it immediately runs the risk of becoming irretrievable. A multi-appendage design, on the other hand, is more redundant. With multiple paddles, if one of them were to fail, in theory, the remaining could still function and allow the device to return to the surface and not be lost to the ocean forever. Once we settle on a multi-appendage design, we then have to ask the next logical question of how many appendages do we want to use? And we can look to biology for inspiration. There are many different organisms that use multi-appendage propulsion across many different length scales. We see things like Daphnia, Krill, copepod nauplii, and Tomopterus, just to name a few examples. And you can see the diverse morphology and number of paddles in these organisms. For the purposes of today's talk, though, I'm going to focus on shrimp and krill and these shrimp-like organisms. They share a relatively consistent body plan across many different length scales, making them an ideal organism to use when trying to look at propulsion across different length scales. They feature a shrimp-like body plan, which is a biological term. And I want to point out let's get the laser pointer up. I want to point out the type of appendages these organisms have. They have two different sets for propulsion. They have thoracopods, which I've highlighted in this diagram in red, which are located on the cephalothorax. And they have pleopods on their abdomen, which I've highlighted in this figure in blue.
Okay, I'm sorry. I thought I got it all.
Okay. And propulsion in these shrimp-like organisms has been studied before. Actually, one of the papers I use a lot is this one that came out in 2011, entitled Metachronal Swimming in Antarctic Krill, Gait Kinematics and System Design by Dr. David Murphy, which very thoroughly documents these stroke kinematics in Antarctic krill, Euphausia superba. Euphausia superba are on the large end of the spectrum, though, being about 6 centimeters in length. If we want to figure out how shrimp propulsion varies with length scale, let's go smaller. Not everything is this large. And so the organism I wanted to look at was Americamycis bahia, which is a tropical species of mysid shrimp, as shown in this figure here. This mysid shrimp only maxes out at about 1 centimeter in length, so a very different length scale than Antarctic krill. So what is it that we expect to see? I have videos in this presentation, and I apologize in advance if Zoom, unfortunately, is dropping frames. But what hopefully you can kind of see here is Pacific krill, Euphausia pacifica, swimming. It's beating its 5 sets of pleopods on its abdomen, one after another in an adlocomotory sequence, creating a metachronal stroke. This is what we're hoping to see. If we take a look at Americamycis bahia, again, I apologize for the dropped frames, but what you'll notably see is there are no pleopods on the abdomen in this organism. Instead, the organism is swimming primarily using its appendages on the front half, on its cephalothorax. It's using its thoracopods to swim. It turns out this is because Americamycis belong to the order Mysidae. And in the taxonomic realm of biology, one of the defining characteristics of mysids of this order is a sexual dimorphism in their pleopods. Males have pleopods. A male mysid, Americamycis, is shown in figure B, but they rarely use them to swim. Whereas female pleopods in figure A are underdeveloped or non-existent in species within order Mysidae. And so in general, these species rely on thoracic appendages for swimming. However, If that were the case, my presentation would be done and seminar would be over. Occasionally, mysids use their pleopods to swim. So let's take a closer look at what's going on and compare a euphausiids appendage setup to a mysids. Again, we're going back to Euphausia pacifica. If we take a look at one abdominal segment in this organism, we can see that they actually have two pleopods. And these pleopods are joined together via a structure called a retinaculum that allows these two pleopods to be in sync with one another, resulting in a 5-paddle metachronal stroke, which is what we see in this video here. Pleopods on Americamysis bahia, when they have them, are actually not connected. They're separate from each other, and this allows for independent motion. In this video, you can see Americamysis swimming using its 10 pleopods, and they're beating independently of each other. I'll let this video cycle through another time, so hopefully you can see it better on the second go. It looks a little bit like a 10-legged walking dog. Again, reiterating that the left and right pleopods in this organism are not beating in sync. And so because we found that this happens, comparing Americamysis bahia to these 5-paddle metachronal swimmers, the krill, the euphausiids we see, gives us a really unique opportunity to compare the number of appendages in a similar body plan in a biological framework. So what exactly did we do? Americamysis bahia are actually commonly used in toxicity experiments in the EPA, and so they're readily available from almost any aquaculture company. We ordered ours in 2 batches, one in 2018 and again in 2020. Pardon me. And we're able to keep them in the lab at room temperature in an aerated tank. By feeding them Artemia twice a day, we were able to keep cultures in the lab for 3-4 months at a time before they started dying out. When it came to actually recording, in 2018, we were unaware of the sexual dimorphism in the appendages in these organisms. And so in 2018, we didn't know what was going on. We captured a lot of videos of thoracopods swimming. In 2020, we wised up. We read the literature and we figured this out. So in 2020, we pre-sorted our mysids to make sure we had males with pleopods because that's what we were particularly interested in. We recorded at a density of 10 mysids in a 1-liter tank, shown in this image here, between 2 orthogonally positioned high-speed AOS cameras, recording at 500 frames per second, that were backlit with infrared light as to not elicit a phototactic response in the organism. Once we had all of our videos, we then had to undergo the monumentous task of digitizing or tracking our videos. And we did that using Hedrick's DLT DV5 software for MATLAB. We created a 28-point digitization consisting of the organism's head, base of the abdomen, and base of the telson. We also tracked each point where the set of pleopods met the organism's body, each midway or kind of knee joint area of each pleopod, as well as the tip of each pleopod. That was a lot of data points. And you can see 25 of those points are in a relatively small area, especially if this organism is a centimeter max as a whole. Our organisms are free swimming, which means we limit any artificial behavior that may occur from potentially tethering the organism or stimulating it to swim. However, pleopod swimming is extremely rare, and there's a high cluster of points in a very small region, making it difficult to get enough accurate videos of pleopod swimming in Americamysis bahia on 2 cameras that are located 90 degrees at an angle from each other. It's not possible to track all 28 points on both cameras. To combat this, we compromised. On one camera where all 28 points could be seen, we tracked all of them, totally fine, exactly what you expect. On the other camera, we only tracked the head, the end of the abdomen, and the telson. Pardon me. And this allowed us to reconstruct the pleopod points in 3 dimensions, assuming that all of the points were rotated equally about the same axis. Once we had our digitization, we then got to extract a bunch of kinematics to determine exactly what was going on. Our final data set consisted of 13 recorded videos of Americamysis using its pleopods to swim. And in videos, we're a mysid underwent multiple strokes, those strokes were averaged together to create one stroke per video. And we were able to extract a bunch of variables to figure out what was going on. Notable ones include stroke amplitude, or angle alpha on this diagram, which is the angle the pleopod makes with the body throughout the duration of the stroke. Angle beta, which is that kind of back knee joint angle for each pleopod. We're also able to calculate beat frequency, pleopod length, pleopod tip speed, phase lag, which is a measure of synchrony I'll get into a little bit more later, and the resulting swim speed of the organism. All right, that's what we did. What did we actually see? As I mentioned, Americamysis only occasionally use their pleopods to swim. Pleopod swimming is uncommon in this organism. In 2018, before we particularly knew what was going on, and we didn't pre-sort our mysids, only 6 out of the 61 videos we ended up recording had pleopods swimming. It only occurred about 10% of the time in our free swimming organisms. The second thing we see when comparing pleopod swimming to thoracopod swimming in Americamysis is that pleopod swimming is fast. This figure shown here is of normalized swim speed in body lengths per second for pleopod and thoracopod swimming respectively. And pleopod swimming is about twice as fast as thoracopod swimming in this organism. Okay, cool. So it can differentiate between its set of limbs if it wants to go fast or if it wants to go slow. But how does, when it uses its pleopods, it compare to euphausiids? Or what exactly is it doing? Pardon me. This set of figures here shows the stroke angles, alpha in the top 2 figures and beta in the bottom 2 figures for the left and the right cycle, respectively, for this organism. The individual lines are colored based on their abdominal segment. P5 is the posterior-most pleopod, and P1 is the anterior-most, closest to the head. And we can see 2 really interesting things from this set of figures. The first, specifically looking at the alpha graphs, pardon me, is that they are actually reflections of each other about the x-axis. If we actually go in and do the math, these cycles are 180 degrees out of phase with each other. This means that one pleopod is always undergoing a power stroke. There's no overlap in which appendage is paddling. There's always one that's doing a downward power stroke, contributing thrust that propels the organism forward. We then have to go in and talk a little bit about the synchrony of appendages. And we do that using phase lag. Phase lag is calculated by the time it takes between adjacent limbs to begin a power stroke. And we normalize that by the duration of the entire stroke. For an organism undergoing perfect metachrony, the phase lag between each set of adjacent appendages should be equal to each other. And so in a 5-limbed stroke, in a 5-paddle stroke, perfect metachrony would have a phase lag of 1/5, or 0.2. If we take a look at the phase lags for Americamysis bahia, this figure here plots all 5 pairings of adjacent appendages. If we look at the left cycle independently, the right cycle independently, and what happens if we combine the 2 cycles together. And you can immediately see that these bars are not equal. Americamysis bahia's metachrony is imperfect. Most notably, this P1 to P5 phase lag in the light blue bar is high across the spectrum, 0.4. However, we haven't really seen this before. Are we analyzing Americamysis bahia correctly? It has 10 appendages, but should we be analyzing its metachronal stroke as one 10-paddle cycle, or as 2 5-paddle cycles that occur one after another? Let me explain that a little better. Imagine in this beautiful stick figure diagram that you're looking at the mysid from underneath, with each of its pleopods coming out the side. P5, again, the posterior most, is in the back, and P1 is up at top. For one 10-paddle cycle, each appendage undergoes its power stroke uniquely. So we start in the back with P5 and then work up the side of the body, P4, P3, P2, P1, and then we cross over to the other side and undergo the same pattern, creating this kind of figure 8 pattern in the appendages. Conversely, if we were to analyze it as 2 5-petal cycles, again, each limb undergoes its power stroke one at a time. However, we analyze each side of the body separately from each other. And so if we take a look at one 10-petal cycle, if that's how we want to quantify this organism's metachrony, when calculating the P1 to P5 phase leg, we're going to use appendages on the opposite side of the body, P1 from the left side, P5 from the right side, and vice versa in order to do that. And when we calculate phase leg using that approach, our phase leg of 0.16 is significantly greater than what we expect for a 10-paddle uniform metachrony phase leg of 0.1. It doesn't appear that Americamycis bahia's metachronal stroke represents a 10-paddle metachronal stroke. If we wanted to analyze Americamycis bahia's metachrony as 2 5-paddle cycles, when calculating the P1 to P5 phase leg, we'll use appendages on the same side of the organism, P1 and P5 on the left side of the organism, and P1 and P5 on the right side of the organism. And when we do that, our average phase leg comes out to be 0.21, which is significantly the same as 0.2. Therefore, we can analyze Americamycis bahia's complete metachronal stroke as consisting of 2 ipsilateral 5-paddle cycles. Ipsilateral meaning they run the length of the body on the same side of the body. Cool. But how does having 10 paddles compare to euphausiids? Pardon me. This figure here plots beat frequency against normalized swim speed for Americamycis bahia in dark blue, in the dark blue circles, Euphausia pacifica, Pacific krill in the gold crosses, and Euphausia superba, Antarctic krill in the gray diamonds. And what we can see from this figure is that Americamycis bahia is able to achieve faster normalized swim speeds than euphausiids. We can actually take this a step further and say that Americamycis bahia doesn't use its pleopods at low speeds, less than 4 body lengths per second. But if you recall back to a few slides ago, that's because it actually doesn't use its pleopods here. This is where Americamycis uses its thoracopods to swim. So it can achieve these low swim speeds, it's just not using it with its pleopods. We can also analyze speed by looking at speed profiles, or the instantaneous speed of the organism over time. This figure up here shows the speed against time for 2 metachronal cycles of Euphausia superba, Antarctic krill. The bars on the bottom of the figure represent when a set of pleopods is undergoing a power stroke. And we can see 2 spikes in speed that actually correspond quite well to when Euphausia superba's 3rd pleopod, P3, is undergoing a power stroke. If we generate a similar figure, albeit slightly more complicated, we have twice as many appendages we're trying to document here. For Americamycis bahia, ultimately, we don't see this. Americamycis bahia have no consistent peak in speed corresponding to any power stroke. There's variations in speed over time, but nothing as dramatic as we see in Euphausia superba. Americamycis bahia is able to achieve smoother speed profiles than Euphausia superba is. The last thing we can do is compare a few non-dimensional parameters in order to gauge how efficient, how well Americamycis is in comparison to other metachronal swimmers. This table here summarizes several non-dimensional parameters for Americamycis bahia, our 2 species of euphausiids, and Odontodactylus havanensis, which is a mantis shrimp. And the first non-dimensional parameter I'd like to look at is the Strouhal number. Strouhal number is calculated by multiplying the frequency by the arc length of the appendage and dividing by the velocity. It's a term we've stolen from fluid dynamics to quantify flow with an oscillatory component. Previous studies have found that when your Strouhal value falls between 0.2 and 0.4, this is considered efficient. We get a maximum thrust output per unit input energy. And it turns out, even in organisms with an oscillatory component, whether it be the flapping wing of a bird or the fin of a fish, biology tends to fall within this 0.2 to 0.4 range. Awesome, animals are great. However, Americamycis bahia's Strouhal number of 0.5 is greater than this efficient range. Okay, let's think about something different. Let's talk about the advance ratio. I've included the formula for it up here, but basically the advance ratio we've stolen from aerodynamics, and it's a ratio of the resulting whole body speed of the organism to the appendage tip speed. And previous studies have found that our advance ratio should fall between 0.1 and 0.6. Americamycis bahia's normalized advance ratio of 0.09 falls just shy of what we expect to see in organisms. However, averages don't always tell an accurate picture of what's going on. So if we actually take a look at how these non-dimensional parameters vary with speed, something really interesting happens. This figure here shows the Strouhal value for Americamycis bahia plotted against normalized swimming speed. And I've graded in that 0.2 to 0.4 efficient area. And you can see that as the normalized swimming speed increases for these organisms, the Strouhal value begins to decrease until it eventually falls within this efficient range at speeds of about 9.7 body lengths per second. If we do the same thing with the normalized advance ratio, as swimming speed increases, our normalized advance ratio also increases until it falls within this expected range that we see in other organisms. And it does this at 8.7 body lengths per second. Analysis of non-dimensional parameters suggests that pleopodal swimming in Americamycis bahia is tuned to achieve these fast speeds. So it's good that Americamycis is using its pleopods to go fast, because it's good at using its pleopods to go fast. So I've thrown a lot of science at you, and I kind of want to back it out just a little bit. I've shown you 4 things, hopefully, that I've found in this past year doing this research. The first is that pleopodal swimming in Americamycis bahia is uncommon, but it results in faster swimming than thoracopod swimming in this organism. Second, Metachrony in Americamycis bahia is comprised of 2 5-paddle cycles that run the length of the organism's body. Third, multiple cycles result in faster and smoother normalized swim speeds compared to 1-cycle euphausiids. And finally, non-dimensional parameters suggest that swimming in Americamycis bahia is tuned to achieve speeds greater than 9 body lengths per second. Research is not done in isolation. And while I've definitely taken a very biological biomechanics approach to this experiment, there's a lot of other ways that this research can be done moving forward. This video shown here is of a Krill bot designed by collaborators, and it actually beats its appendages at in the same range of Euphausia superba. As I mentioned, we're interested in defining stroke kinematics for a multi-appendaged approach to robotics, and we can see that they're starting to be utilized in devices like the one shown here. Using these devices and also using techniques from fluid dynamics, we can also go in and take a look at the hydrodynamics that results of metachronal swimming. So we can see how flow structures vary in response to things like stroke amplitude, beat frequency, synchrony of appendages, length scale, all the fun parameters that we care about. And so we can continue to ask questions about how the hydrodynamics of metachrony change in response to these different parameters. Coming back to the purely selfish scientific research aspect of it, using robots also allows us to push kinematic restraints to their extremes, to things we might not actually be able to observe in biological organisms. So we can take it to the next step and see if there's an optimal set of kinematics that we don't observe in biology, whether that be through a measurement of the amount of fluid an organism is able to move, or how fast that organism is able to move. We can fine-tune things using robotics that we can't actually see in organisms. We can also go in and compare metachrony across different length scales. Within organisms, we can see how changing stroke kinematics can result in a different swimming behavior and a different swimming mode in these organisms. We can also see how stroke kinematics vary with length scale. And we can go in and ask a purely hypothetical, never thought of this before question: do stroke kinematics better reflect the length scale or the swimming mode of these organisms? Stay tuned. This is chapter 2 of my dissertation, not today's talk. We also can compare the geometries of metachrony in different organisms. I've really only focused on shrimp-like organisms, but other things do this as well. We also see metachrony in copepodnopoli. We see it in things like ctenophores or comb jellies and in Tomopterus. And so we can see how things like the number or the orientation of these appendages affect propulsion when comparing across different geometries. We can also ask questions about how flexible paddles may compare to rigid paddles. Tomopterus have gelatinous paddles, but our shrimp, our krill, have rigid paddles. Pardon me. And we can also see if there are any consistency in morphological design between these organisms. How does the length of the paddle compare to the length of the organism? Or how does the spacing between paddles vary? Is there a constant to that? This is a really interesting field of work that has a lot of interdisciplinary potential between biologists, ecologists, engineers, everyone you could possibly imagine. And I'd like to close by acknowledging the fact that this field is actually on the uptake. I was able to present this research at the Society for Integrative and Comparative Biology in January of last year in a symposium specifically designed for metachronal propulsion, of which this paper was published as a part of. And I also got to help co-author another state of the field metachrony paper. I really wish this video were playing. It's a beautiful time lapse of ctenophore metachrony, but I suspect it's not showing up super well for all of you. But I'll leave you with that. And I think I'll take any questions. I'm not sure how this part is supposed to go, but that's me. Thank you.
An applause for Melissa. How fascinating. Oh my gosh.